Okay, let's start. So before I start teaching electric fields, there's something interesting to note in the world of physics. It's not just A-level physics, maybe even FSC. You're going to notice that physics has these topics which belong to different fields, like what we've studied up till now, circular motion. I think that goes more with mechanical engineering. Gravitation, well, it's for physicians and maybe the future astronomers or the people who work in space related fields. But now we're going to do electric fields. And this is for the future engineers. So if there's any people here who want to be engineers in the future, you're going to enjoy this topic. And I think one of the ways to really figure out what you want to do in the future is to see which chapter you enjoy more. I personally think that I enjoy engineering chapters more as compared to, I don't know, chemistry chapters, but I like chemistry as well. So instead of just learning physics just for the sake of marks, I think note these things, pay attention to these small
Hey,
details. Anyway, electric fields is one of those chapters in which I have actually tried diving into this chapter when the quarantine started, when lockdown and everything started, before actually getting into teaching, I wanted to learn all A-level topics in detail. And when I was learning this chapter, I realized that I have been learning this chapter the wrong way. I thought that this is about electricity, but before I start teaching this, I want to make sure that you guys know that there's two types of electricity. The first one is static electricity. This is static electricity. The second one, it's called current electricity. For those who have done AS, you have studied this part, right? You have studied current electricity already in AS, but you did not study static electricity. And the fun fact is, when I was learning this topic in my school, I did not know the difference between these two. I thought that they're the same thing, but that's just not the case. I'm going to give you an example right now, and you're going to know what I'm talking about. So the first one is obvious. Okay, before I say, so Usman, we literally just started this topic, right? Okay, anyway, when we were children, we used to do something. So all of you had these rulers, scales, and we used to rub this on our hair. Like if this is my hair, I don't know if I can make a nice hair. So we used to rub this, we used to rub this, and when we rubbed this on our head, we noticed something. So let's say I have rubbed it on my hair now, and now suddenly, if you have small pieces of paper, you're going to notice that this scale, it attracts these pieces of papers. And that's not something that you can just take for granted. It doesn't happen just because it happens. It happens because it's a phenomenon. It is called static electricity. But how did humans discover it? Now, since this is one of those chapters in which I have actually dived in, I'd like to give you a little bit of insight. Okay, so this is basics. Now, let's make a heading. I mean, we don't need a heading. All right, electricity goes way back, even before the very first AD. I'm sure you guys have studied history. So right now it's 2020. Before 180, literally the first year of this calendar, you could say, we had a person. His name was Thales. He was a scientist. Now, he discovered something. When he rubbed amber, what is amber? Basically, you know, you're not supposed to note this down. It's just to tell you guys what amber is. In trees, there's this little weird thing, and it's called amber. You can search up on Google. I might show you later. But he rubbed amber with silk. He rubbed amber with silk. I mean, obviously, you know what silk is. And he observed something weird. When he rubbed amber with silk, after that, silk had a charge on it, and amber had another charge on it. And you guys know right now, I mean, it was later discovered that there's a negative charge and there's a positive charge, but they started attracting each other. So Thales was the first person to discover this phenomena of electricity, just for the sake of it. He rubbed amber with silk. You're not supposed to know this down. This is just for basics, but I think we should really learn what actually happened. So he rubbed amber with silk, and that's when humans discovered electricity and they started attracting each other. Now, obviously, the history is very big, and we're not supposed to go into that. But Benjamin Franklin is the person who named the plus as positive electricity, and he named the minus as the negative electricity. Back then, humans did not know that there's two types of electricity. There's a positive charge and there's a negative charge. But Benjamin Franklin was the person who did that. Now, in O level, you did a lot of experiments, right? I'm not gonna teach you that, but just a little reminder, like a little recalling thing. Do you guys remember this? Like this ball right here, this sphere. And when we brought a negative charge, let's say, when we brought a minus here, then the charges used to, separate. Do you guys remember this? O level. So let me make this in another way. So the positive charges go to the left side and the negative to this side, and then they connected with the earth and they discharged it. And yeah, basic stuff. But obviously that's O level. Now, let's see what A level teaches us about electricity. Let's start. A level electricity. Gauss's law. This is the first thing that we're gonna do. All right. Oh, I think I added an extra S here. The first A-level thing, A2 thing I'm going to tell you about is electric field strength. The reason I'm teaching electricity right after gravitation is because these two chapters, they are very close to each other. You're literally going to see they're twins. They have such similarities, you're going to go crazy. Okay, electric field strength. I think that's spelling, LOL. All right, so in gravitation, you guys studied this, right? I know it's like really similar. In gravitational chapter, you studied this, right? This G. This is called the gravitational field strength. And just for the sake of it, the formula for it was Gm over R squared, right? But in electricity, just like we had G in gravitation, in this chapter, we have something that's electric field strength. Now what's the definition? Electric force per unit positive charge. In gravitation it was force per unit mass, but now we're not talking about masses, RV, we're talking about charges, and that's why it's electric force per unit positive charge. And at the end of the chapter, in fact, maybe in the middle, I'm going to tell you a very big difference between static electricity and current electricity. In this chapter, we're more concerned about charges, not the currents. You're going to notice that. Now, what's the formula for it? Well, it's E is equal to F divided by Q. You can make a big Q, you can make a small Q, that's your choice. Now, if I would like to display this concept, so you can better remember it, it would be like this. We have a circle here and a positive thingy here. This is the positive charge, and we have an arrow like this. And I think you guys can better imagine it now. Force per unit positive charge. That's electricity. I mean, that's electric field strength, right? Note this down and tell me when you're done. Are you guys done? Are you guys with me? Hey, come on, guys. What about the rest? Are you guys done? We literally have 8 students, and I have 2 replies. Come on, Rubef, okay, so we have an answer from Sabina. Abdul Wasi, Aisha. Okay, great, perfect. I am clearing this, and let's do the next concept. The very first concept. Okay, now the second one. All right. Okay, electric field. Electric field, everyone. We just did electric field strength, and now let's see what electric field is. Now, just like gravitational field, in which a mass experiences a force, electric field is a region around the charge in which its force can be experienced. Basic AS, I think you guys have studied what types of electric fields there are. You know, do you guys remember this? Non-uniform, uniform, straight lines, parallel lines, 90-degree angle, all of that stuff. What is the unit of electric field, by the way? Come on, guys. What's the unit of electric field? Do you guys know? All right. The unit of electric field is NC. Why is it NC? Well, because I think this is basically the main unit of electric field strength, force per unit charge. Charge is in coulombs and Newton is the force, right? Okay, now there's a little note that I want to make, and this is a really good comparison. When we talked about gravitation, we talked about attractive forces, right? We did not really talk about repulsive forces. So if I want to show a direction of my field lines, I would say that all of them are inwards. So if I want to make a mass here, you know, small m here, all of the arrows would be pointing towards the mass. And that's what I mean when I say attractive force, right? LOL, I again made the wrong m. Okay, so this is the mass, and we have some arrows which are pointing towards this mass, like this, like this, like this, and basically just a basic idea. You're supposed to know this, by the way. They may ask you this, though I don't guarantee this in A2, but it's pretty obvious that it's going to come in AS. All right, so a little note along with GFL, gravitational field lines. Okay, I'm going to write this for you guys. So this is basically gravitational field lines. Gravitational field lines. And they're going to be always inwards. All right, electric field lines. Okay, can anyone tell me, can you guys repeat this for me? Are electric field lines gonna be in one direction or both directions? Is electric field attractive? Is electric force attractive? Yes, it's both, meaning I am gonna make 2 diagrams. I'm not gonna make one. So we're gonna make 2 charges. The first one is gonna be for plus Q, and the second one is gonna be for minus Q. And this plus and minus, this is the reason why electric field is in both directions. If electric field was, I don't know, like if electricity had only one charge, it would also be in one direction. but since we have two charges, they're going to be different directions. So that's how we're going to make the arrows. And here we go. And that's the basic diagram. So tell me when you guys are done making this. All right, tell me guys when you're done noting this down. Okay. I am gonna erase this now. All right, I'm gonna represent something in a diagram, and it's gonna make a lot more sense what A2 electricity is gonna be like. I'm gonna make a charge here, and obviously, since I have a charge, it's gonna have some kind of electric field. But my question is gonna be, I mean, not for you guys, we're gonna do it, we're gonna do this together because I haven't really taught you this. So this is a point, and this is the radius from the center, and we want to know the electric field strength. How do I know that? Well, let's write a formula. So electric field strength is going to get multiplied with area, and we're going to have charge here, and we're going to have a new term here. I'm going to explain this later, but this is the basic formula that relates to charge, electric field strength. This is electric field strength, EFS. So if anyone asks, this is electric field strength. I'm going to write this, electric field strength. Now, what in the world is this? For those who are doing A2 for the first time, you are going to get confused, but don't. This is what I call, this is what all physicians and all students call relative permittivity of free space. And the value for it is 8.85 into 10 raised to the power minus 12. Just like in gravitation, we had a constant which was capital G. Here we have this. I'm going to explain what this is in a second. Okay, so what is relative permittivity of free space? Yeah, basically this is electric field strength, and I forgot to tell you what A is. This is symmetrical surface. Oh, that's an extra M. I mean, that's one less M. Okay, symmetrical surface around the charged object. And this is the charge on the surface of the charged object. When I say charged object, I'm talking about this right here. Now, this is a formula that I literally just stated to you. We're not supposed to derive this at this moment. So this is electric field strength. This is area. If you multiply E with A, you're going to get Q divided by E. This small e with a dot E naught, this is relative permittivity of free space. And I'm going to explain this to you in a few seconds. This Q is the charge on the surface of the charged object. I hope this makes sense now. I hope this makes sense now. If you're doing this for the first time, you're going to have to remember this formula. Now let's minimize this and let me explain you what I mean by relative permittivity of free space. Now, permittivity, doesn't it sound similar to the word permission? So this comes from the word permission. And I mean, if it's talking about permission, it's obviously talking about the allowance to do something. I don't know if I phrased this right. So imagine that we have a charge and it has an electric field. Now, we know that there's different types of space, right? We have vacuum. Now, what I'm about to tell you, you're not supposed to know this. You're not supposed to write this, right? You are supposed to know this, not in A level though. So imagine that you have vacuum. I don't know if the spelling is right, LOL. Vacuum, air, right? Vacuum, air. And we know that in both of these, I mean, the density and all that stuff, it's different, right? So I would not be wrong to say that if I were in vacuum, this charge would not have the same electric field as this, because we know that every space has a different permittivity of free space. Now this E naught, this is relative permittivity of free space. Just like in chemistry, we have relative molecular mass and that stuff, we have relative permittivity of free space, and the standard for it is the vacuum. So the relative permittivity of free space is, the base for that, the standard for that is the vacuum, and that's where they found out this value from. So you can imagine this like this. So I guess charges flow, right? But at all kinds of different spaces have different rates at which they flow. I'm going to talk more about this later, maybe in tomorrow's class. For now, I'm going to leave this at this because this is a completely new concept, and new concepts need some time to absorb. Now, we're done with this part right here. Now we're going to derive the formula for electric field strength for a charge, for a spherical charge. Now I know that the formula is this, but can anyone remind me, what's the formula for the surface area of a sphere? What's the formula for this? What's the surface area formula for a sphere? Come on, guys. SA, surface area of a sphere. Basic math. O level. Exactly. 4 pi r squared. Good job. So if I want to write the area, I'm going to write 4 pi r squared. So it's going to be E 4 pi r squared is equal to Q divided by E naught. And the formula for electric field strength is going to be Q divided by 4 pi E naught r squared. All right, and this, I am going to do something here, and I'm going to introduce a new constant. I was wrong to compare E naught and G because the more logical comparison is of what I'm about to do. Now, you can see that in this whole formula, we have some things which are just constant, and this is it. This is a constant value. It's constant. So if I want to show that I have something that's constant here, I would go about it like this. E is equal to 1 divided by 4 pi E naught. Then I'm going to do multiplied by Q divided by R squared. Now, this thing right here, this is constant. And that's where I introduce a new constant, which is E is equal to K. So it's going to be KQ divided by R squared. And this K, this is the new constant. So your final formula, I mean, you can use both of them. It's your choice. But we can also write this formula like this, KQ divided by R squared. I personally think that this formula is actually better because it makes stuff a lot easier for us. So K is equal to 1 divided by 4 pi E naught, and this value is equal to 9. I think it's actually 8.99 into 10 raised to the power 9, but we can write it like this, and that's a correct way to represent it. So it's a new constant, K. Are you guys with me? Does everything make sense so far? If you didn't get anything, you can ask. Now note this down, and we're gonna do the next thing. Yes, I know that. Okay. I mean, thanks for telling. So, all right, so I'm about to erase this, everyone. Clear. Okay, now I have a question for you guys. Let's say I have a line of charge and we have a positive charge induced on this line. My question for you is, what is the electric field around this charge gonna look like? Is it gonna be a circle? You tell me the shape. What is the electric field gonna look like? What do you think? I need an answer from everyone. Sabina, when you say straight, what do you mean? You mean like exactly where the charges are? That's where the electric field is gonna be? Okay, what about the rest? What do you think? Is it gonna be a circle? What is it gonna look like? All right. Okay, that's interesting. Well, check this out. This is what basically, maybe I did not use the appropriate terms, but this is where the electric field is going to act around this strip of positive charge. I made it a little big, so let me fix it up. It's going to be like this. I'm not asking for electric field lines. I'm asking for electric field. And this is the region. I'm going to make two circles, one here and one here, and now it's going to make much more sense. Oh my god, the drawing looks terrible. Let's just use a circle. Okay, this is much better. I should have used it before. All right, it looks much better. Okay, that's the first one. It's going to be a cylinder, and I'm going to explain how. I mean, it's an obvious concept in physics, but I'm still going to talk about this. Okay, so something like this. Now let's add two lines like this. All right, now why is it like this? So if I made it in 3D, it would be something like this. So imagine that I have a charge. I'm looking this from above or from below, right? So this would be our strip. Am I right? This is a strip, right? This is a strip if we look at it from above or from below. Now, we know that every charge is gonna have an electric field around it. Am I right? It's gonna have an electric field around it, right? In the form of a circle. Now, if you translate that into this whole shape, that's what it's gonna look like. So if I had only one charge, it would be a sphere. But if I had a lot of charges in a line, in the form of a line, it would not be a sphere anymore. It would look something like this. It would be a circle, but because it's a line, there's a lot of these circles, and we end up with a cylinder. Did this make sense? If it did not make sense, I can repeat this. Are you guys with me? Does it make sense? So yeah, just imagine, okay. So if I have a single charge, right, electric field around it would be in form of a circle, right? This would be the surface of this. It would look like a sphere, right? But Now I don't have one charge anymore. I have a lot of these charges. I have a lot of these charges in the form of a straight line. Now, what I said was, imagine that you are looking at this line from above. If I'm looking at this line from above, it would look something like this, right? It would look like this. But now I know that I know one thing, and that's this. Around every charge, we have a circular region around which the electric field acts. Now, since this is a line, and if I move it, if I rotate this, I don't know if I can rotate this, but if I kind of rotated this like this, right? Do you see this? This is from above. Now, I'm gonna rotate this and, okay, let's make the 3D version now. And when I make the 3D version, it's gonna look like this. We're gonna have a lot of these circles and we're gonna end up with a cylinder. We're gonna end up with a cylinder. And here we go. And this is the cylinder. Yeah. And this is the line. This is the strip. All right, I hope this makes sense now. So imagine this as a 3D version, but let's go back now for a second, just for the sake of it. And now I am gonna bring it back to the version from above. And here we go. And that's why we get the cylinder. So for singular charges, a lot of things are different, but I'm not really sure if you would get this question, but if you would get, it would be something like this. The area you would use for these combined charges. Now you have combined charges. Okay, the meeting will end automatically, so just saying beforehand, the area is going to be 2 pi RH because that's the surface area of the cylinder. So if you ever get a lot of charges and they ask you to tell the area or calculate the electric field, you would use this A. All right, guys, the meeting is ending on its own. See you guys in the next meeting. I'm sending the link immediately. Okay, so I would like to correct something I said before. I said that permittivity has to do something with the flow of charges. I would like to correct that. I don't know why I said that. That concept is wrong because this whole chapter is about static charges. Charges are not moving here. So it's not about flow of charges, but permittivity has to do with how effective the electric field strength is. It has to do with electric field strength. It has to do with force. I'm going to get into that again right after we do force. For now, there's something that I have to clarify, and this is also a concept in A2 electricity. Check this out. So when I have a charge, now for gravitation, it was kind of different. The gravitational force, it appeared as if it was coming from here, right? And a lot of us assume that it's inside the earth, right? Now, we're not going to discuss whether that's correct or not. For charges, however, that's not the case. For charges, all of the charge, it's concentrated at the surface. It's at the surface. So if I have a charge here, the spherical charge, all of the charge is going to be on the surface. We have no charge inside it. Like literally, we have no charge inside this. Like if you imagine a charge as being a sphere, like I don't know if I can make a 3D thingy here. Okay, let's just let me try at least. So if this is a sphere, right? Let's give a little 3D field here, like, a 3D ball. It looks awful, but so this is a 3D ball, let's say, right? Now, imagine that I somehow was able to open it. And if you guys are thinking that, okay, so what if I got inside the charge? Well, yes, you are right. If somehow you managed to enter a spherical charge like this one, you would experience nothing at all. Like you would be enjoying, you would be having an amazing day, and all of the charge would be at the surface. So the inside would be, it would not have the charge, right? So just a fun fact. But this, however, is more of a concept. So let's make a little note. I mean, let's erase this first. Now this is a proper note. So yeah, make sure you don't miss noting this down. Electric field. Yeah, so why is it? That's because electric field inside a conductor is zero. So I forgot to mention that if you were inside a charge, you would not feel anything because electric field is zero and all of the charge is on the surface. So electric field within a conductor is zero. All the charge is on the surface. Are you guys with me? Does this make sense? Because a lot of students ask, okay, why? Well, that's a very good question, but we're going to discuss that when we study the force and the formulas for the other things. In fact, I'm going to tell that later. Why? Proving with the formula. All right, let's minimize this and let's move this to one side. By the way, back in the day, they did not have these values. So just a little, like, don't forget. So a little note, don't forget. K is equal to 9 into 10 raised to the power 9, and E naught is equal to 8.85. Yeah, so yeah, 8.85 into 10 raised to the power minus 12. LOL, I kind of forgot for a second there. Okay, yeah. I don't know, for some reason, I always remembered this, and I would say that as a student, it was one of my biggest mistakes. I should have remembered both of these, but I had this always at the back of my brain, but I kind of did not keep this in my mind because this was always available in the data booklet. So back in the day, they did not mention the value of K. So the students always had to remember this separately, but now these values are included in the data booklet, but it's always better if you keep this at the back of your brain because it's just going to be easier for you to solve the questions. Now, the next concept. There was this man, his name was Coulomb, Coulomb, a physician, a scientist, Coulomb. Now, this man, we know his notable contributions to science related to electricity, but we don't know what he exactly did, right? But what he did was he created a law which was later called Coulomb's law. And what is that law? Let's look into that. We're going to do the Coulomb's law specifically right after this, but he did introduce a law of force between the charges. Now we know that there's a formula for force, which I did not tell you yet, LOL. So yeah, I have to tell you the force first. Okay, let's do the force first and then do that. Okay, yeah, the Coulomb thing comes after. Let's do this first. Apologies, I introduced something I was supposed to tell you earlier. E is equal to KQ divided by R squared. Before we do the first thing we want to do is this. E is equal to KQ divided by R squared. Now, K is a constant, and we can say that Q is also the same for one charge. So therefore, E is inversely proportional to R squared. Just like G is inversely proportional to R squared. And it's a very nice deja vu for you guys because G, that's an inverse square law. But here, it's like very similar, right? Similar. And again, Gm divided by R squared. Just check out the similarities. Mass, charge, constant, constant. radius square, radius square. These similarities are like very important. So as you move away, the electric field becomes weaker. Okay, I'm gonna make this small, and I'm gonna move this to one side. Okay, are you guys with me? Does everything make sense so far? Because now we're gonna do something. Okay, I'm gonna have to erase everything. So are you guys done noting this down? Hey, is everyone done noting this down? Come on, tell me. Because I'm about to erase this. Don't tell me, bring this back later. Okay. Now, before we go to that Coulomb thing, we have to make some graphs, just like we always do. But we're gonna make a graph for the positive charge first. And that's a very interesting thing about electricity. Back in gravitation, we only needed to make one graph, but now it's two graphs, specifically for the same reason, because we have two charges, positive charge. The first graph I'm gonna make is gonna be it's gonna be the same for the other one. We have an arrow like this, and we have E here, and we have D here. Now, I'm gonna ask you something. This is the surface of charge. Is it gonna be a straight line? Is it gonna be a curve? Or is it gonna be a curve like this? What do you think? Or is it gonna be like this? Last option for geniuses. Which one of these would you say is the answer? Just tell me the color of the line. Or I can just number them for you guys. So this is 1, 2, 3, 4. Okay, which one of these is gonna be the answer here and why? Keeping in mind, okay, I'm gonna ask someone from you guys. So let's ask Legina. So Legina, which one of these is gonna be the graph for E and D? What do you say? Which one of these is gonna be the graph? I literally just told you the relation. Okay, that's the correct answer. Good job. It's gonna be 1. Look guys, before teaching you this, I told you that E is inversely proportional to R squared. Didn't I tell that, right? I had a reason for telling that. And when I say that E is inversely proportional to 1 over R squared, you should have remembered that when I was teaching you gravitation, I taught you G. That's why I mentioned this in the first place, because the graphs are gonna be similar. Okay, 1 is the answer. So we're gonna make this right here, and we're not gonna touch this. Now, is it gonna be a straight line here, or is it gonna be a curve? What is it gonna be here? What do you think? Behind the surface of charge, what is the graph gonna look like? Straight. Okay, think about it. What is gonna be the graph behind the SOC? Come on, guys. I need an answer ASAP. Okay, let's ask. Okay, Sabina. Okay, she's here. So Sabina, what is it gonna be? Is it gonna be a line? Is it gonna be a curve? Or do you have another thing that you would like to offer? Okay, so far we have, oh my God. Abdul Wasi, why did you change your answer? Look, it's gonna be 0. That's the correct answer. And why is it the correct answer? Because I just told you that for all charges, E is 0 inside the charge. Don't forget this. Let's make a little brain here. My chemistry teacher does that a lot. So let's make a little brain here and never forget this. I mean, I gave that on purpose. So, you know, E is 0. Never forget. Yeah, that's more than enough exclamation marks. E is 0 inside a charge. And if it's 0, now there's two options for a line answer. If you say your answer is line, it's either going to be this or it's either going to be this. So if your answer was this, I mean, you're not even supposed to make a line here because it's literally 0, right? But just for the sake of showing it, let's just make it. So if your answer was this, I mean, if your answer was this line, you're correct. But if your answer was the other line, meaning constant, that's incorrect. So never forget it. Now, another statement. Note these things down, and I'm going to write a statement here. Let's make this small. Okay, let's move this here. Now, I mean, yeah, I'm going to write it because you guys might forget it. Positive plus VE and minus VE charges, they're going to have different graphs. By the way, when you go to the university, you're going to be doing a lot of comparisons between gravitation and electricity. So keep these points at the back of your brains, like E is equal to 0. This is one of those things that really matters. So Usman says, why not horizontal line above where curve is starting? Because Usman, you know, no, I'm still going to answer that. It's because if I make a straight line here, I am technically saying that electric field strength is constant. And this is like, I don't know what number is that, but that's a very huge number. You are saying that inside a charge, you're going to have the max E, and that's just not right. Anyway, I'm glad you got it before me telling you. Okay, now, plus VE and minus VE charges will have different graphs. A very important point that I had to mention. Now let's make the graph for the minus charge, for the negative charge. All right, so what is this going to look like? Is it going to be the same or is it going to be the different? Yes, that's what I was waiting for. It's going to have a different direction. So I'm going to make a line here. And this line is for the surface. And it's going to look like this, like literally the opposite of what we made back there, and a red line here to show that this is a continuous graph. This is E and this is D. That's what it looks like. Yeah. Negative charge. Okay, and I think we can finally get into the Coulomb's law. All right, so Coulomb, Usman, what happened? What are you asking? Are you asking why is the graph going to be like this? Please elaborate your question. When you say why, what do you mean? Yes, so 1 second. Like, come on, man, make a negative charge, make a positive charge. Is it gonna be, are both of them gonna be like this? No, minus is gonna be like this and plus is gonna be like this, right? And that's why even their electric fields, they're gonna have negative directions. I know these are lines of force. I know these are lines of force, but a negative, oh, okay, LOL, what am I saying? Basically, a negative charge is a negative charge. You can also say that this is one of the reasons, but look at this. E is KQ divided by R squared, right? So, I mean, come on, if I have a negative charge, I'm obviously gonna have a different graph with a different direction. So keep these 2 points, right? the lines and the charge. Because it's a negative charge, it's going to have the graph in the negative direction. Why? Another reason, just for the sake of it, plus, minus. All right. Now, the plus one and the minus one, they're not going to have the fields in the same direction, right? So if this has this direction, this one is going to have this direction, right? So both of them are different because here it's moving away from the charge, but here it's coming towards the charge. It might have not been the best example in the world, but this should make sense now. Logical reason, it's a negative charge, that's a positive charge, and they have different directions. Okay, finally, the Coulomb's law. I'm erasing the graph. All right, so Coulomb's law. All right, so in 1875, the magnitude of force between two electrically charged bodies was studied by Coulomb, and he came to a conclusion. Force is inversely proportional to r squared. He noticed that the force and r squared, they are inversely proportional. And this is called an inverse square law. Inverse square law, or just like I wrote here, oh, it's Coulomb. Coulomb's law. Right, so the formula that he came up with was something like this. Now let me explain you how in the world we got this. Oh my God, okay. Here we go. Now, electric field had a formula which looked like this. But I know that force is, right, so electric force is EQ. That's just a basic formula that you're supposed to know. Electric field strength, charge, so E is F divided by Q. And I think I told that in the beginning. Newton per Coulomb, right? So FE is equal to EQ, right? Now, I'm going to substitute something here. I'm going to substitute the E above over here. So this is red, and I'm going to substitute this here. So after substituting, I'm going to end up with something like this. Multiplied by QR squared, multiplied by Q. Now, this is a constant, right? But we can say K too, but let's go with this for now. And you're going to end up with this. FE is going to be equal to 1 divided by 4 pi E naught. And we have QQ divided by R squared. Now, it's time for some recalling here. Check this out. FG, by the way, I'll give this opportunity to you guys. What is the formula for FG? Come on, what's the formula for FG? Hey guys, what's the formula for FG? Come on, it's an easy formula. Come on, I need an answer from you guys. Okay, yes, GMM divided by R squared. Great job. GMM divided by R squared? Or should I say G into MM divided by R squared? Doesn't this kind of look similar right here? Force between two charges, force between two masses divided by the square of their separation? Exactly. Both of these are very similar. So yeah, just a little fun fact. But electric field can be both attractive and repulsive. But gravitational field can be attractive only. It has not yet been discovered that gravitation can be repulsive. Are you guys with me? We're gonna do one last thing, and after that, that's gonna be it for today. But let's do this thing. Now, if you guys are done with this page, tell me in the chat so I can know if I can erase this. All right, I'm clearing this up. Okay, that's weird. I just got a notification that tells me that I have, oh yeah, it's showing 9 minutes for me. Yeah, so we have 10 minutes left and the timer shows 9 minutes. Well, that's because I had to rejoin the meeting. Anyway, let's make 2 charges. Oh my God, it turns out I have not been recording at all. Okay, I have been recording. It's so weird. Huh, it shows me that I'm not recording. That's weird. Anyway, this is plus, this is minus. Now, if I want to make an arrow to show the point charges, the direction towards, I mean, the direction towards of their motion. I mean, if we have 2 charges, they're going to be attracted towards each other, right? But if we have a plus and plus, they're going to repel. They are going to repel. This is plus and plus, and they are going to repel. So let's bring these a bit closer here. Now, this thing right here, this is going to be the radius. This is going to be r, and this is going to be r as well. This is going to be the radius r. Now, this is just a display of what the electric force looks like. And QQ are point charges. Now, there's a little advice or a note that I'd like to make. If they ask you to define, you know, electric field or force, use 1 divided by 4 pi E naught. But if calculation based, use K, right, just for your ease. So K is going to be 9 into 10 raised to the power 9, just like I said before. All right, I'm going to give you a question and you're going to do it by tomorrow. We're going to discuss this tomorrow. So we have 2 charges. This is 10 microcoulombs. This is 5 microcoulombs. And we have a point A. Now, I know this looks kind of confusing, but if you actually look into the question, it's not that confusing at all. Now, this is the separation of 10 centimeters. And this distance is 2 centimeters. Now, my question for you is, calculate the electric field strength at point A. Find the electric field strength at A. So this is your homework for tomorrow. Do this, and yeah, we're gonna discuss this tomorrow. Okay, are you guys with me? Does anyone have a confusion so far? You can ask me. Okay, that's great. Okay, tell me when you're done. Okay, Sabina, okay, I see. I'll wait for you. So yeah, tell me when you're done and I can turn this all to white. All right, is everyone done? Can we end the meeting now? All right, I take that as a yes. So see you guys tomorrow. Tomorrow we're going to discuss the question, and yes, make sure you are revise the topic, you know, and solve the question. See you guys tomorrow. Allah Hafiz. Have a nice day. Bye, guys.